Hello and welcome to my presentation on limb prosthetics and its advancements. Next. So let's go over some device history first. So compared to other medical devices, prosthetics has a pretty decently long history. So the first prosthetics were probably some wooden contraption, but those things wood doesn't last long through history, unfortunately. The earliest evidence we do have, the earliest prosthetic here is called the Cairo toe, found in Egypt, very aptly named, dated 3,000 years ago roughly. The earliest leg prosthetic was dated to roughly 2,000-ish years ago. That was made out of bronze and wood attached to the human body using straps. The reason why they're classified as prosthetics as opposed to more for looks was that there was flexure built into the object. So as you can see here, there's basically early semblances of a joint. And that classified it as a prosthetic as opposed to something like a mask, just to cover up some more for appearances. Let's move on to major developments. Basically, the usage of prosthetics greatly correlated with an improvement in surgical amputation survival rates. So the adoption of techniques such as using tourniquets, as well as using antiseptic techniques, greatly increasing the rates of survival after amputation, also greatly increased the usage and the need for prosthetics. Because if you don't survive your amputation, I guess there's no need for prosthetics. Kinoplasty is a concept of rearranging muscle and bone structure to make it more compatible with the prosthetic that you're planning on attaching. So preserving more of the muscle tissue and bone tissue so that you preserve more control over the eventual prosthetic you do attach. You don't want to get rid of the entire arm, for example, if you can just get rid of the forearm. As an extreme example. The knee joint preservation, for example, was only popularized after this time, 1958. And that was to preserve more function, because earlier it was easier to just cut off at the femur, but later on they began pushing, and advancements in medical techniques made it so that the knee joint was preserved if possible always, and that allowed for basically more control of your prosthetic and less reliance on the prosthetic itself. So it's like putting more work on the human body. But basically, furthermore, advancements also were drastically spurred after every war. So every war, there's a bunch of veterans that require prosthetics, and there's a need and a demand for better prosthetics, more prosthetics, and that's what occurs after every war. So
is now on the same
it's kind of
plane as the
interesting.
former knee.
So this is
with
a
the foot and
example,
toes
I guess, of kinoplasty. I guess less so kinoplasty, but just an example of how to modify the human body so that it is more compatible with prosthetics. So in this case,
pointing backward and the heel
they just have to remove
forward.
the femur, and they kept
Because of the rotation, the
the
ankle
rest.
bends in the same direction as the knee. The surgeon will take into
Actually, I
account
don't know if
the
you guys
age
can
of the
hear
child
this.
and their growth potential. Initially,
But basically, they removed the knee, but they saved, I guess, the ankle joint, and they reattached it to the remaining like quad and hamstring, so that eventually, when they grow up, they will be
knee center will be
at
lower
level
than
with
the
the
unaffected
knee
As
once
the
grown
child
up.
grows
Oops.
and bones lengthen, the knee centers will match.
So then the knee centers will match, and after
In
that,
3 to 6
they can
months
then
after the bones have healed,
they
the
still show you.
patient can be fitted for a prosthesis. The patient's foot
See, there you
fits
go.
inside the socket of the prosthesis, and the ankle functions as the knee joint.
So yeah, essentially the ankle, the surgery makes it so that the ankle then functions as a knee joint, because the knee and the femur, the knee and the good chunk of the, I guess, tibia had to be removed.
Time
So
is
this is an
now
example
on
of
the same
advancements.
plane as the former.
Next. So current relevance. So what is relevant right now? There's an aging population that's increasingly unhealthy. According to NIH stat pros, more than 150,000 patients undergo lower extremity amputation. So this is just lower extremity, just like your leg or foot, be amputated every single year. It's a huge number. A lot of it attributed to diabetes and other diseases, which are increasing in rates, which are increasing rates. Increasing? Okay, yeah, increasing. Furthermore, wars keep happening. There's more veterans, wounded veterans every year. That also requires more prosthetics. Furthermore, children who get prosthetics need to get multiple prosthetics throughout their lifetime as they grow in order to match their growing leg length. So that's also more prosthetics, and therefore there's like a demand and a growing market for this medical device. Move on to medical device design. Materials. Obviously, like all wearable medical devices, it should be lightweight and durable. Lightweight but durable. So plastic is a great material for this, especially since it's now 3D printable. Because it's 3D printable, or like 3D moldable, plastic moldable, or injection moldable, you can you can more customize and create a prosthetic faster, faster and more customizable. And some of the materials include aluminum, titanium, and silicone, which are lightweight, either lightweight and durable or comfortable. Furthermore, there's an increasing number of prosthetics being tested with electrical components, such as electrodes, motors, and microprocessors, which we'll cover a little bit later. So let's go over a diagram of the device. So the interface, only so much time we have. Okay, the interface, there's 4 core parts of most prosthetics. Even though they look different, they all have essentially these 4 core components. The interface, which is the contact between the device, the device and the human body has to be comfortable, not irritating. Suspension, how it attaches to the human body. In this case, it's with a harness. Structural components, such as the joints, as well as the control cable, control housing. These are all structural components that are crucial to hold up, to give mechanical properties to the prosthetic. And finally, appearance components, so that it is more human-like, if that's desirable, or if it's more like user-friendly, for example. Another example here, leg prosthetic here. Interface would be the socket. Suspension, in this case, would be the suction with the vacuum that attaches or connects the socket to the human leg and connects it tightly. That could be a strap as well, but it depends on the company. Structural components would be like the knee joint, the shin tube, the housing. And the appearance components, as you can see here, the right side diagram picture, they have more emphasis on making it look like a human leg, as opposed to the left side, which is more, I think, like athletic oriented, maybe performance oriented. I think I've seen athletes wear these. All right, device classification next. Currently, most prosthetics are classified as Class 1 under this regulation number, 890.3420. So then you search that up in the Code of Federal Regulations, 890.3420, and you can see here external limb prosthetic components. You get an identification as well as a classification, or the definition of all these prosthetics, all these subtypes of prosthetics, as well as the classification. In this case, it is Class 1, and the device is actually also exempt from this thing called 510K as well as CGMP. So 510K is a requirement to show that your device is similar to a device on the market already. And CGMP is basically to make sure that there's quality assurance in producing your device. So these two are oftentimes required, but in this case, for prosthetics, it is exempt. Class 1 is also the lowest classification, which means the least stringent requirements in order to be allowed to market your device, your medical device. So just a really simplified diagram here. General controls are required of every single classification of devices. So Class 1, Class 2, Class 3, they all require general controls. General controls just means there's a baseline requirement. It meets a baseline requirement for safety and efficacy in using the device, to make sure it doesn't kill anyone, that it's safe for consumers. So all 3 classes, all devices passing through FDA are required to meet these general controls, and then a lot of devices are required to meet more than that. Oftentimes, prosthetics are Class 1 general controls, and they're also exempt. There's some limitations, but for the most part, it is a much simpler process compared to a lot of other medical devices to get to market. Other devices, more complicated devices, require applications of other things like the pure market approval or 510K, and that costs a lot of money or a lot of time, or both. So there is a caveat though. There are more complex prosthetics that have motors and electrodes, and that's an electrical component, and that kind of makes it more into electronic, as well as a mechanical device, right? So now there's an increased stringency of regulation. So now the classification is bumped up to Class 2, and now is no longer exempt. As you can remember in the previous slide, it could be exempted even as Class 2, but this Class 2 is not exempt, and requires special controls on top of the general controls. Basically more stringent when you incorporate motors and electricity into the device. Next, let's cover major manufacturers. holy moly, there's a lot of manufacturers. A lot of these are international. A few of these are national. Something interesting I thought was that two of these bought clinics in the U.S. where they directly make the prosthetics and fit them to the consumers, cutting out the middlemen. So there's a lot of, I guess, middle class people getting hurt by this. It's kind of unfortunate. Now moving on to the journal article that I covered. It is titled "Improved Control of Prosthetic Limb by Surgically Creating Electro-Neuromuscular Constructs with Implanted Electrodes." So this is relatively recent, I believe 2023, in the Science Translational Medicine journal, journal. And here, a brief synopsis. Basically, patient had to be amputated above their elbow, so they lost their elbow, wrist, finger joints. Many joints were lost. Okay, that doesn't leave them much to work with. What they had to do, what they did in this study at least, was that they surgically split up the existing, what's left over, the nerves that are left over, and attached them to the existing muscle groups, as well as an extra muscle that they grafted from a different part of their body. So they split up a nerve and they connected it onto different muscle groups in the leftover stump in this person's arm. And over time with practice, this patient was eventually able to gain more control over each of those nerves and muscles, which are paired up. And in the end of the 2-year study, it enabled the patient to do all this amazing stuff with a motorized arm, of course. So this is not like a normal prosthetic, which is a class 1. This would be a class 2. But this is just to show what the next step would be. So this is a really, really recent study. And I think this is a growing area of interest. And has been for a few years. So this is all done by flexing certain parts of the muscle that's left over in that little stump there. Or in that stump there. Oops. Not little. Sorry. This is just to further show that the neuromuscular electrical impulses were found to be significantly stronger after more practicing and more usage of those muscle groups. So at first, with when the nerves were first paired with the muscle groups, there wasn't too much flexing. However, with over 2 years, the person got really, really good at flexing those muscles and got really good at controlling his arm, as you could see in the earlier video. So the signals here became stronger. These are electromyographs, so electrical impulses to the muscle. So relevance and interest. So why is this? Obviously, this is quite interesting. The whole thing to me, especially the robotics component. But why is it relevant, right? So the reason why it's relevant is because it brings us closer to a fully articulated prosthetic, blending like what is and what is not part of our body. Eventually, basically, you won't be able to tell what is. It gets so realistic that you can't tell that it's like a robot, like a robotic part or mechanical parts, which I think is just freaking cool. And I think definitely will help a lot of people blend in more with society or feel more comfortable if that's how do they feel, And furthermore, in this study in particular, they showed what's possible, like what's anatomically possible by the human being, by basically splitting up these nerves and through neuroplasticity, I guess, being able to control a lot more muscle groups in what was used to be just a bicep, triceps, and flexing those two muscles mainly. So just using that little part of the arm, this person could control the entire prosthetic arm to a very high degree of specificity. And the goal here is to basically get more control always. As you can see here, the elbow is not moving. So the control is only at the wrist and the fingers. All right, next. Just a quick summary. There's a long history that correlates with success rate and survival rate of amputations. They all share a few core components, but have diverse appearances based on the company that makes them. The fitting production design, everything's getting more complex and more like high tech, especially with 3D printing. Everything's a lot faster and a lot more customized for the specific user. It's a class 1 designation with many exemptions, which has a low bar for entry. So there's a lot of companies making these prosthetics, a lot of competition, at least with non-motorized prosthetics, which are the bulk of prosthetics right now. There are a lot of guidelines for non-mechanized prosthetics, but only one actually for motorized arm prosthetic. So as advancements are made, regulation will also be put into place, I assume. The future also hopefully will allow for higher degrees of control, some more specificity control to replicate all degrees of freedom that's possible using our human arm. And it's becoming more of an interdisciplinary problem, whereas previously it was more mechanical engineering. Now it's like a bit of everything: mechanical, electrical, biological. Just because you have to interact with either the nerve interfaces that are remaining in your arm, or interact with like the muscle components in your arm. So a lot of different fields combined. I think it's more biomedical than ever. And I'll end off with this. My concern, always healthcare costs, because no matter how advanced a design can be or a device can be, if people cannot access it, it's not affordable, then I think it's kind of pointless. So this is always a concern, and hope this thing becomes more accessible and affordable in the future. I think the future is very bright. So references, and thank you so much. Please leave a question or questions on the discussion board, and I'll talk to you guys soon.